We'll continue today with our previous class in which we started the introduction of the transport layer. Just a little revision of what we did in a previous class. We understood that transport layer provides the logical communication between applications as compared to the network layer, where a network layer provides the logical communication between the hosts. Also, we saw that transport layer protocols are implemented in end systems only. No other intermediate node, whether it's a stands what transport layer is all about, doesn't have the protocols of transport layer. So network routers do not act on transport layer fields basically. Then we went through the different protocols that we come across in the transport layer. Two main were UDP, that is user datagram protocol, which is unreliable connectionless service. And also we saw TCP, which is transmission control protocol, which is reliable and connection oriented. Then we briefly discussed about the functions. I think we wrote them somewhere. This we all understood. Yes. Here are those functions. We started with process level addressing, that is the port mechanisms, TCP UDP ports, then multiplexing, demultiplexing, segmentation, packaging, reassembly, connection establishment, management and termination, acknowledgements and retransmission. This we use for reliable delivery, flow control as well as error control. It also supports maintaining integrity, setting up and tearing down of connections, virtual circuits, and also it provides abstraction. Examples that we took was TCP, UDP, SPX, network link, ATP, BNP, and NetBIOS. Now, to begin with, we'll go about explaining each one of the functions that I had mentioned in the previous class. And the first one that we'll come across here will be multiplexing and demultiplexing. So let's understand what is multiplexing and demultiplexing. Now, in the picture here, what you can see, we have, just a moment. Okay, we have in between a server and we have at the two ends, this is one client, this is another client, and this is a server. So a client has these protocols which is given here, which I marked in red, and then we have the application layer. Obviously, application layer is the topmost layer if we go bottom up, and application layer gets the data from a higher layer, a higher process, that is the a process that is running. So if we have a process running inside the system here, it provides data to the application layer. Now in this case, we have, let's say, processes like Skype, Netflix, or a browser here, which is a Firefox given here. Now this process, let's say Skype, okay, has a door through which the data passes from the network to the process and vice versa. This door here, let's say for example here there is a door in the process. This door is we call as socket. So a process has a socket which is a door through which data passes from the network to the process. So if you are sending across the data from the application layer into this Skype, it goes through the socket. And if you are sending from the Skype to the network, it has to go through this socket. So it's like a door. So transport layer in the receiving host, that is here, in the case we have this server here. So if Skype has sent across the data through the socket, it goes to the transport network link physical, then through the physical link, and in the server it would be received by, let's say, Skype's main server around here. It goes up through physical link data, and it would enter inside through the socket. It will enter inside the process that is running in the server through this socket. Socket. Each transport layer field has each transport layer segment has a set of fields in the segment. The job of delivering the data into a transport layer segment to that of a socket, that is what I just now mentioned here. I mentioned this in the pic. Transport layer, which is here, gives the data to the application here, which is, let's say, Apache HTTP server. In the case, for example, you had an HTTP request from web browser. The job of delivering this data here into the socket, that is the door for the process, this is what we call as a demultiplexing. Demultiplexing. Okay. And the job on this end, we have this as a door or a socket to the application, this as a door, and this as a door which already has there. Now, the job of gathering the data chunks with the header information to create segment and passing this segment to the network layer is known as multiplexing. So let me denote the data here with a blue field. So I got a part of data here, blue. I got a part from this socket. I got a part from this socket as well. Now, gathering this part, and this part together, and then forming a segment from the data of this, and then adding its own header here, attaching it with the packet here. This forms an overall segment. This is what we have, segment, and this part is known as multiplexing. So on this end we had multiplexing. On this end, once this part would be delivered back here to the application, removing the header, we call this as demultiplexing. The job of gathering data chunks with header information to create a segment, which is shown here, and passing the segment to the network layer is called multiplexing. The left hand side. On the middle one, this is the job of delivering the data in a transport layer segment to that of a socket is called demultiplexing. Now what do we have here as a socket? Let me clear annotations. Okay. You can see here multiplexing and demultiplexing. How part of an application is sent differently. Multiplexing at the sender, handle data from multiple sockets, add transport layer header, which can be later used for demultiplexing. Also, demultiplexing at the receiver, use header information to deliver received segment to the correct socket. So, how does the demultiplexing work? To understand here demultiplexing, first we would need to understand socket. The term which I have used here is socket. Socket. Now, socket here has a unique identifier. And what is that identifier that we have? That is the source port number and destination port number. And what are these? These are special fields that indicate the socket to which segment is to be delivered. And each port number here, we have a 16-bit number. Now we are discussing about port numbers. Each port number, so port number is a 16-bit number. And what does it say? That means it ranges from 0 to 65,535. This is the range of the port number. It ranges from 0 to 0. And among this 0 to 65,535, we have 0 to 1023. These are restricted or reserved. Means it cannot be given to others. Means different applications. For example, you create an application and you want to give a port number. Among 0 to 1023, you cannot give that. Why? Because they are known as let me just change the color of it. They're known as well-known port numbers. And what we mean by well-known port numbers, it means they are reserved. These are reserved. And what are they reserved for? They are reserved for well-known protocols. What are well-known protocols? For example, HTTP. What is the port number of HTTP? 80. Everybody knows it. That's why it's reserved. Another example, FTP, a well-known protocol. So 21 has been reserved for FTP. You cannot take it and put it in some other application. There is RFC, request for comments 1700. You can find a long list of well-known port numbers. Okay, so how does demultiplexing here now work after knowing what basically this socket is? We have two parts that would identify us an application to which the data is being sent. One is the address of the host, which is given by the IP address, and other is the address of the application, which is given by the port number. So combination of IP address and the port number would help us to direct the segment to the appropriate process that is running in the client system, right? So it's mentioned here as well that host receives the IP datagram. Each datagram has a source address and a destination IP address. Each datagram carries one transport layer segment. Each segment has a source and destination port number. Let me erase this and we'll see how it would look like. This is the TCP UDP segment format. Okay. This is how a transport layer segment would look like, in which there are different parts. The first part that we see here at the bottom is basically the data which you have received from the higher layer, which you are supposed to deliver it. This is the application data or the payload. Then the second field that we come across is header fields. It's written other header fields. Why? Because there are some fields which are different to UDP, some fields which are different to TCP. So what we will do is we will be taking each segment format separately. We'll take TCP's header format as well as UDP's header format. That's why it's mentioned here as other header fields. And the third part within the header itself, this is part of the header, this is all a header, is source port number and the destination port number. Source port number and the destination port number. Since it's across 32 bits, so we have 16 and 16, each port number having a 16-bit address, 16-bit port number. This is which tells us the information about from which application it's been sent and to which application it's to be delivered. By IP address, you would reach the destination, but after reaching the destination, to whom this segment should be passed on, this is where the source and the destination port number helps us. Okay, I hope this is clear. Any questions till now? Can send it across the chat. I had a question sent by, let me see if I have that question here. A message was sent by whom was it? Ahsan? Is he around, Ahsan? Ahsan, are you listening? No, I don't think he's here, but I'll read a question so he can just watch it and he'll get the answer as well. So he says, if I entered facebook.com, it need to be resolved by DNS server to get the destination IP for the data packet. Then he says, how my request reaches DNS? I first need to know the address of DNS itself, where I get that address so that the domain name I entered is resolved to it. So his question, Ahsan's question started from here. The communication is established between two nodes by sending and receiving data packets, say across internet. But how a data packet knows where I can find the search result means how we know that the destination IP address, as there are a number of nodes connected to internet. How does our data packet know the destination IP address in advance? This is his basic question. So if you remember, when we took, I'll first answer this question and then we'll move ahead with our transport. If you remember, sorry, when we took the data link layer, in the data link layer, when we were doing framing, then we had to put the header of the data link layer we had to put the destination MAC address. That was the physical address. There we discussed ARP. That is how we will get the destination, how we'll get the MAC address of the destination, how it would change from router and so on, and how it is changed within the frame that you have made. Basically, ARP would give us the MAC address. But for IP address, if you remember, I said that in order to send a packet to the destination, let's say to your friend, you would need its IP address before you actually send it. Now that there are two things, like you play a game, you tell your friend what's your IP address, then you create a server and he joins in, you know the IP address, you key in, and that's how you'll start doing it. But you knew the IP address, right? In other situations, like Izhan asked, like, how do I know the address of Facebook when I'm logging in, when I'm going to facebook.com? You actually do not know the IP address of the server of Facebook. It would be difficult for a human being to remember so many IP addresses in a dotted decimal notation. That's why for us, it was easier to remember a word like Facebook, like Google, like Yahoo, and so on, so that you can type in that and you'll get the result. Now, how it's then done? You had domain name systems, DNS. What was the help that DNS provides? You give in the Yahoo address or Google address, and DNS replies back to you with an equivalent IP address of that domain. So domain name gets converted into an IP address. And then with the normal networking, the routing, you would reach to that IP address, the routing that you've studied. Once you go to that IP address, it replies back to you and then communication starts. Now, another question is, how does our packet know what is the DNS of it? For this, if you go back and remember DHCP as well as manual configuration in IP address, I said that if you manually key in or if you have DHCP, DHCP sends you an information by which you can get connected to the internet. And what was the information that you get by DHCP? The first one was IP address, all right? The second one was subnet mask. The third one was default gateway, means that your first hop router or through what IP address you should route all of your packets to. And the fourth information also that was given there was that of DNS. So you gave primary, secondary and tertiary DNS there. So you yourself are mentioning to what DNS should your packet look for. How should your system get the equivalent IP address for the domain name? You are telling your system, go to this address. There are plenty of free DNS available. There are some DNS which have been given by default by your internet service providers. Like if you're using BSNL's broadband, check out that you will have some DNSs which are given by them. In fact, DNS, there are Anycast DNS also available. Okay, you need to put that in your router, in your broadband router, what you are using. Okay, Anycast DNS works with major sites. And how would Anycast DNS help? It does direct caching and peer services to you, and it would make it much faster than a normal DNS. So basically, to reach to the server, you would need its IP address. To reach to that, to know that IP address, you have a domain name. All right. To convert that domain name into IP address, you need to know to which domain name server you are sending your packets to convert it. And that you will put within your system as DNS configuration primary and secondary. I hope that answers the query that was sent by Isham. If you still have any doubts, please message me again. All right, now moving back to what we were discussing here. This is super, okay. So it mentions here connectionless demultiplexing. We'll take this what connectionless is. Let's first take this UDP, that is user datagram protocol. Let's first try to understand what UDP is. Now, UDP says that I do not have any connection establishment. I do not maintain any connection state. I'll just type in here. Why UDP? The question is, why UDP? If we know that UDP is unreliable service, why UDP? The first is no connection establishment. What we mean connection establishment? After this UDP, we are going to study TCP. TCP uses three-way handshake in which you have to send the communication, receiver says, yes, I accept it, then it goes back, acknowledgements and so on, and then that's how connection is established. Okay, for those who joined late, we are discussing now UDP and TCP, all right? The first part that I'm taking is UDP, that is user datagram protocol. What I am explaining this time is why UDP? When we know that UDP is connectionless service, UDP is unreliable service, it's like extending the best effort service of internet protocol. Packets can be lost, packets are delivered out of order, but still we use UDP. The answer for this is number one, no connection establishment. What is connection establishment? TCP does it with three-way handshake. We are going to take that in detail. UDP does not establish any connection, which means it starts right away. How would that help? No delay in connection establishment. And where would we use this TCP? We would use UDP in those applications where we want minimum delay. And where do we want minimum delay? For example, you are watching a cricket match online. Okay. You would say, okay, even though some packets are lost, let's say even though some frames are lost, but you would want that when a ball is bowled, it should be right away shown to you. You don't want that, I want all the frames, I want the best quality, HD quality, but even if it's this time, next over and you are still watching the last over, no, you would want the delivery to be timely. Why? Because this is an application which is a real-time application. Real-time applications require minimum delay. Regardless of whether the packets are out of delivery, packets are lost, it's not reliable. This service requires timely delivery. That's why UDP would help us because there is no connection establishment. The second thing about why UDP, there is no connection state. What we mean by no connection state? When TCP is established, when TCP makes the connection by three-way handshake, it has to then maintain a connection state in the end systems. And connection state means I am connected to this, um, system. There are send and receive buffers. There are acknowledgement parameters. There is congestion control. There are a lot of things within it. Okay. It's like you log into your mail and then you're connected with your mail. You keep the session and all those things connected within it. And then you ensure that if your mail has reached, it has reached completely. So why TCP? In those applications, you would ensure that whatever has been sent to me, it's sent completely. Like you have an attachment in your mail, let it download, let it take time, but I want complete message to be delivered as compared to UDP where you want in a timely service. So in UDP, when we say no connection state, we do not have to maintain any connection state. It does not track any parameters. And what parameters? Like I said, buffer, send, receive buffer, parameters of congestion control mechanism that we have, acknowledgement, sent and acknowledgement, parameters that we have. Number 3, there is a small packet overhead. I mentioned that at every layer there is some work done, and whatever work has been done, the information is kept within the header. So this header would help us to, identify what work has been done by that layer, like demultiplexing, multiplexing. This information should be mentioned within the header. There is a small header for UDP as compared to TCP. Why? TCP has to have three-way handshake. TCP has to do congestion control. TCP has to keep the buffers for send and receive, acknowledgement, and so on. Since UDP does not track any of these parameters, so UDP has a small packet overhead. Small packet overhead means lesser transmission time, lesser delay. TCP's header size is 20 bytes as compared to this UDP header size is just 8 bytes. Remember this well. Keep this in mind. Keep this in mind. This also means that UDP does not have much work to do on the data that has been given by application. It creates the segment and passes on to the network layer, which also means when UDP immediately passes the segment to network layer, sorry, it has a lesser delay. While as TCP has to add stuff like congestion control and so on, it would take more time in processing as compared to UDP. So where do we use UDP? Real-time applications requiring many minimum detail. Examples of UDP protocols: RIP, that is routing information protocol, the SNMP, network management, DNS. In fact, keep that in mind. DNS is UDP. Why? We want minimum delay. That's why DNS is UDP. Multimedia applications that we have is UDP as well. As compared to this, if we have TCP, email services, web, file transfer, they are all belonging to TCP. Any questions till now? No questions? Let me just clear this part and let's move to the next one. So this is the reasons which I just mentioned. No connection, it's simple, small header size, no connection state, no congestion control. UDP can blast away as fast as is desired. And these are the applications. streaming multimedia applicant, loss tolerant. Loss tolerant, when I mentioned that even when the bowler is bowling in a match, you're watching it online and some frames are lost, doesn't matter, but you want it timely. Okay. This is the RFC, that is request for comments, which mentions UDP, User Data and Protocol, given by J. Postel, and it dates back to 28th August 1980. And I think all of you were not born. I don't think anybody from my class was born by then. So this is how UDP would work. Let us first see if we have UDP segment structure given here. Here we have the UDP segment structure. And what is the UDP segment structure that we have? This part which I'm highlighting in red is a header. How much is header? Just now mentioned 8 bytes. And the rest of it, which I would highlight in green, this is supposed to be data. This is the application data. This is the message that the process actually wants to transmit. Now coming back to the header. The header has 4 fields as is visible here. The first field being the source port number. The second field, the destination port number. Each one being of 16 bits. Or 2 byte field 2222, making this a total of 4 fields. And then after this we have the length and the checksum. What is the length and the checksum that we have? The total mentioning the length of the field, and the checksum is for error recovery. We have taken checksum before this as well when we are discussing errors. There we mentioned that we have internet checksum, and within internet checksum when we are discussing, at one point I said this is done by the transport layer, and this is where we use the internet checksum. In fact, there were examples also which we took for checksum. There was a video link which I had provided you explaining how we get the internet checksum, the one which had one's complement and so on. This is how a UDP datagram would look like. Quite simple to understand, nothing much within it. So this is the 4 fields and the data. If you remember here, UDP checksum, the goal is to detect errors. We have taken this previously, so I want to repeat this part. It's an example of UDP checksum. I believe you revised that video and we will be. Let me go back to understand how this would work. So this is how UDP works on a transport layer. This is the action. So SNMP server passes the application layer message to the transport layer. The transport layer here uses SNMP in the form of UDP, and it puts on the header, attaches the header to the SNMP message. So SNMP message here would be the application data which we just now took on, and the header, that is UDP, and this subscript of H means header of UDP added to this. So it's the transport layer header that has been added. And what would be within it? The 4 fields which we just now took. of 2 bytes each. The source port number, the destination port number, the length, and the checksum. And it's added to the message. It's passed on to the network layer, that is IP here. IP passes on to the data link, which passes on to the physical link. Physical link passes on to the link that connects the IP cloud to the source as well as the destination. It's routed across, and the SNMP client, once it receives, it gives it to the physical layer. Physical layer passes on to the data link layer. Data link layer passes on to the network layer. Network layer passes this to the transport layer. So transport layer would take out the header of UDP, get the destination port number and source port number, by which it would do demultiplexing. It would understand that this message is to be given to this destination port number, which is given here, as well as it would look for the checksum and see whether there is any error within the message or not. After doing all those things, it would pass on the SNMP message to the SNMP client application. Demultiplexes the message via the socket. And if you remember previously, we said transport layer communicates with the transport layer like this. What was this? This was the logical communication. But actually, how did it send it? It sent it like this. So this is logical, this is actual communication. So this is basically what UDP is, how UDP would work. And we took examples of UDP segment as well. Taken this checksum previously, so I'll just move on. In summary, for UDP, UDP is a no-frill protocol, which means segment or the datagram of UDP can be lost. It can be delivered out of order. It's the best extension of best effort service of the, in which it says that I'll send and hope for the best. I'll try my best to deliver it, but I don't keep any promises whether I'll be able to really deliver it, and whether I'll be able to deliver it on time. It might be lost and so on. But the good thing about, if there are disadvantages that we see in UDP because of being unreliable, but the good thing is that it has minimum delay as compared to TCP. There is no setup, there is no handshaking, and there is no maintenance of that connection as well. It can even work. Network has, errors, packets lost within the network, it can still work. There is a bit of reliability, that is the checksum, which checks for errors. There can be built, additional functionality on top of. We will see that. The next part, before we go to the TCP, that is the Transmission Control Protocol, is the principles of reliable data transfer. How do we understand this reliable data transfer? So we have a sending process here, we have a receiving process here, and the application layer passes on to the data of the transport layer, and transport layer provides a reliable channel or a reliable service abstraction in which you can send a reliable data over an unreliable channel. So if the network layer cannot provide certain reliability, here